Technologies and Micromanufacturing webinar. Our webinar today is entitled Meeting Today's MicroMilling Challenges. This is Don Nelson. I'm publisher of Micromanufacturing and Cutting Tool Engineering magazines. I'll be serving as moderator. Today's presenter is Ralph Piccolo, who is Vice President of Sales at Cimatron Technologies, a leading provider of integrated CAD/CAM solutions for mold, tool, and die makers, as well as manufacturers of discrete parts. Ralph began his career in 1978 as a CNC programmer. He subsequently worked as a plant manager and an applications engineer. He joined Cimatron Technologies in 1996. Ralph will be discussing the trend toward milling part features with tools as small as 1/10 of a millimeter in diameter and the challenges this creates in terms of materials, machine tool requirements, and generating complex tool paths. The presentation will take about 30 minutes or so. It is being recorded, and you will be notified when it is available for review. Ralph will answer as many questions as time permits after his presentation. He will respond to all unanswered questions via email. To submit a question, type it into the GoToWebinar box at right and hit the send button. Ralph, I'll turn things over to you now.
Okay, thank you, Don. Thank you, everybody, for attending this afternoon. Today's agenda will go through what is micromilling, the industries and applications that are using micromilling, the technology, definitely the tooling and the CNC programming. Starting off with what is micromilling? Machining with superb surface quality within tolerances as tight as 0.0001 millimeter, using cutting tools as small as 10 microns or 4/10 of an inch. The micromilling machines have high-speed spindles up to 25,000 RPM. I did read an article about the University of Florida that is working with a direct spindle that'll go 500,000 RPMs. This whole market is really crazy. Along with the micromilling, you have to have very accurate machine tools with repeatability and location and all that stuff. Again, the cutting tools have to be very accurate, and they're cutting materials as hard as 80 Rockwell. Quite a bit is going on in this industry. These machines, they go from 2-axis through 5-axis. Again, spindle speeds 25,000 or 250,000 RPM and up. Positional accuracy is very, very tight. The acceleration of 2G force on that. Maximum feed rates. Again, as we get into this further, you'll see why all of this is a requirement for these machines. Also, the tool monitoring system, the picking up the tool, monitoring the wear, the load, the growth on the spindle, and then the machines also the controls. They have to be able to process tremendous amount of data very quickly. They have to, be able to look ahead and see what's coming when you're getting into corners and turns. Some of the industries that are using this application, the medical, dental. If you notice there on the left, that ant that's on it's kind of hard to visualize, but that's actually a chessboard with all the pieces on there. So these are how small things are getting out there. Electronics, rapid prototype, engraving. We're even seeing machining of electrodes out of pure copper. Jewelry, and also in education, we see a lot of research and development being done on this new technology and the new machines and cutting tough materials and the type of cutters out there. Some of the applications, this one here was stainless steel. These posts were 8 thousandths in diameter. They were 60 thousandths high, and a 30 thousandths end mill was used. It was, you know, again, real small stuff. This one here was brass. You know, those cone shapes in the middle there, the wall thickness is 3 thousandths, and around the whole edge on the outside there, there's 8 thousandths diameter holes. So you can imagine, you know, how tough it would be to cut these with these tools, and how accurate you have to be. Now, if we look at the MicroMilling Challenges, the world is getting smaller. There's a tremendous increase in demand for manufacturing micro-scale components. You know, and every day there's new challenges with new materials. They're coming up with new and different molds, coating. Again, they're milling parts, 0.1 millimeter diameter tools. They have to achieve, you know, micron level accuracy, and when these parts are that small, they have to come off, you know, completely done. So the surface quality has to be, you know, way up there. They're measuring these things with microscopes, and it's quite amazing. Some of the opportunities you can see here. There's you know, a small part there. There was a 2-shot mold, and another one which was an insert mold for the electronics industry. A lot of people are looking into this as a niche market, so they can, you know, have some competitive edge, because not everybody's able to produce tooling or produce parts, you know, this small. Now, if we look at the micromilling machine requirements, the machine is only good as its weakest individual component. It's definitely less forgiving than traditional milling, and each machine component must be suitable for the requirement of tasks. You know, if you're cutting real hard material, then you're going to have to look at different tooling rather than using you know, standard tooling for, you know, softer material. So, you know, there's a lot to consider. If we look at some of the things that you should consider if you're investigating micromilling, you know, the bed and the architecture of the machine. You know, again, when you're holding microns and you're cutting with, you know, 2, 3 thousandths, 1 thousandths, you know, 4/10 cutters, you know, every bit of vibration is going to affect what's happening. Also the temperature, you know, of the room and the parts, and definitely the spindle, you know, what type of spindle, and, you know, what happens when you change tools, how accurate is it changing the tools. So there's all kinds of equipment to monitor all of this as you know, running these machines. The drive and motion technology, you know, how accurate is it? I mean, these machines move so fast, they have to get to the point. You know, is there backlash? You definitely have to have high acceleration, and you know, the guide system definitely got to be repeatable and consistent, and you can't have any wear on your guide system when you're trying to hold microns. Another thing to consider is, you know, how you're going to hold your parts, how you're going to clamp them. You know, you got to be able to quickly interchange parts. You have to be, you know, very accurate on when you're putting in the second, third, fourth part. And again, on the controls and monitoring system, tooling. You know, when these spindles are in there forever or in there for a long time, and you're cutting. You know, we did one test with a 6,000 ball cutter that cut for 12 hours. Well, you know, is the length of that tool changing? What's the wear on the tool? You know, what's the force? Is it running out? You know, all of this has to be monitored while you're cutting. And again, these controls have to be, you know, very fast and process a tremendous amount of data in a short period of time. And then, laser pickups. They're using laser pickups for picking up the part, locating the part, monitoring the tools. There's quite a variety of different tools out there. I'm not an expert on the tools, but if you look here, these are, it goes from 1,000 to 19,000 diameter. These are now standard tools that they have on shelf that you can call and order and get. This is, it's definitely a growing market. The picture on the right is a 4/10 tool next to a human hair. That's what people have used on some of these machines. And what we feel is a big requirement for micromilling is the CAD/CAM system. First of all, when you're bringing in data, you have to bring in the data as accurate as possible. You can't have any little gaps. Any little mismatch is definitely going to show up. Also, the system must be able to handle tight tolerances, machining strategy. You have to have a tremendous amount of tool control so you can cut these parts the way you need to cut them based upon the material, based upon your cutter, and based upon the results that you're looking for. One of the other very important things is the knowledge of stock. If you can imagine that you're cutting with a 2,000th diameter cutter and you're removing a bunch of material, well, when you go back with that next tool path, you better know exactly where the stock is, because a half thousandth of stock could break that tool or not. So, that's very important. Also, these tools aren't real long. You're getting real close to the part, so you have to be able to track the tool, the holder, and where all of this can fit into the part. The CAD/CAM requirement, these machines are, like I said, 2-axis and 5-axis. Your CAD/CAM system must support, the multi-axis machines. Again, the data translation, gaps and mismatches are going to cause you problems. You're not going to end up with the result. The system should be able to read native format, bring the data exactly as it was designed. It's real nice to have an integrated CAD system, so in the event that you have to do some modeling of a holder or a fixture, you can bring that right into the CAM system. The CAM system then can recognize that the workpiece is there, and the stock and the holder and your fixture. The CAD and CAM system must be tuned and optimized to support the following requirements. Tight tolerances. Again, geometric tolerances of 0.1 micron is very, very tight. The algorithms to produce the tool path, the smooth tool path, has to be there. And definitely these machines need a tremendous amount of point distribution throughout your tool path, so it has to be able to support that as well. And you definitely want to be able to round and smooth all of your tool paths, whether you're approaching, whether you're trying to get into a corner, or just changing directions. You must have rounding of the corners. And again, smooth and accurate tool paths. This picture here is basically we took a traditional CAM software and we created a tool path with the same tolerances, same side step. It was a 0.6 millimeter ball with a 20 micron step over. And you can see here the spikes on the left versus a nice smooth tool path. Now, those spikes are measuring, 0.4 micron. Doesn't sound like very much, but when you look at this part under a microscope, you're going to see all of that. some of the machining strategies that you should consider as well too. You definitely have to have intelligent tool paths. Constant chip load is vital to using the tool the most efficient way. Again, I'm going to say several times the knowledge of the stock. Where do I go? How much do I cut? And feed optimization. What happens when you get into that extra couple of tenths of material? Do you want to just continue moving on at the same feed, or do you want to slow down? Tool control. You have to be able to cut these parts, at 80 Rockwell. You can't just cut it like you normally cut anything else. You have to attack it slowly, and you have to have the most efficient tool path. The tool motions, high-speed machining options where you have the trochoidal or rounding corners, rounding rapids. All of this is vital when you're cutting with these small tools. Clean between passes, clean between layers. Knowing all of the information about the stock and where to go is real important, but also the motion to get there. Now back to the knowledge of the remaining stock. When you throw one tool at it and then you go to another tool, you don't have to create boundaries or remember, or what some people end up doing is cutting the whole job with the smallest tool and cutting it very slow because they don't want to try and figure out where they have to go or forget an area. Again, the less operator interaction when the system knows what's been cut and what hasn't been cut. Again, tool holder and spindle tracking. You want to use the most efficient tool that you can. In this particular picture here, you can see that the tool's not getting all the way down to the bottom of that pocket. You don't want to end up cutting the whole job with a real long tool and cut it slow and worry about the tool breaking. So, the CAD and CAM system has to be able to say, I'm going to take the short tool, I'm going to cut everything I can, but when I grab the long tool, I'm only going where the short tool couldn't go. So the short tool can get 80% of the job, maybe even a little bit more, 90%. The long tool can get the areas that couldn't reach. It's much more efficient on the machining time, and you're not relying on the programmer to remember to go back and get every little area. Also with the multi-axis, with the 5-axis, again, these real small tools, you're attacking these parts in different angles, different directions. A lot of times you have to get better surface quality. Also, again, once you start tipping your tool and moving around the part, you better know where that stock is. So if you cut it from one side and go to the other side, the software must be able to know that, hey, that's all gone. I don't have to waste time cutting air. Now, if we take a few minutes and look at some examples and some tool path strategies, I'll turn it over to John.
Hello, everybody. Can you see my screen, Ralph?
Yes, now I can.
Okay, great. Okay, so I've got just a couple of examples today. The first one that I have here, I've got some dimensions on the screen so you can see how big the part is. Not terribly big. Let's see. If I zoom in on this area, you can see that along the outer perimeter of the part, I'm going to have a cutter that's going to be less than 10 thousandths to get inside there. But obviously, there's areas where bigger tools can go, so we're going to kind of whittle it away with a series of cutters. And I've got just 3 in this example right here that we're going to calculate live. So let me go ahead and launch this first one. Okay, so the first tool path is 30 thousandths flat, and it goes in and it roughs out the center area, but obviously the tool is too big to get into these other areas, and we'll point that out a little bit better in a second. Let me open up the second one, and what I'm going to do is I'm going to go to my tool library, and this is a 20 thousandths ball cutter. I can get a feel for the size of that tool if I position it on the part, just to kind of understand it. Is this tool really going to be able to fit into these areas? But this is only one of a couple ways that we can determine whether or not this tool is the right size for the task. In fact, before I show you that, let me just point out one thing. Being that we're doing the micromilling, you'll see that my decimal places here are 6 places. So when it comes to the amount of material that I want to leave or the step down, we can get all the way down into 6 decimal places for those types of parameters. But what I want to show here is the preview. Now, this particular procedure has not been calculated yet, and even so, we can look at some things. Let me just open this window up a bit more. If I look at the previous stock, this shows me what the last tool left for this procedure to cut. And I can also look at the remaining stock. This would be a preview of what this is going to look like if I were to calculate this program with the settings that I've chosen. So you can see that it's showing us that it's getting into some of these areas. And then lastly, we can also see the excessive material, and this points out where that tool is going to encounter some heavy areas. So let's go ahead and calculate this one. And you'll notice that, like Ralph was saying, I haven't had to draw any boundaries or tell the tool where to go and where not to go. The system is taking care to track the stock. So you'll see that, for example, in the center area where the 30 thousandths flat was able to go, obviously I don't have more roughing motions there. But over here, obviously the 30 thousandths flat didn't go there, so I am getting these roughing motions. But still, the tool is too big to really get into the ends of the veins. It's going down a bit out here, but we're still a long ways from finishing this outer perimeter in the teeth of the gear. And let's execute this one. And while we're waiting for that, I'll elaborate a bit more on the tool library. Like Ralph was saying, for the tool library, we can have specific libraries for various materials so that in micromilling there's so much testing goes on to have the appropriate down step, side step, RPM, and feed rate. And the tool suppliers actually do a great job of supplying the recommendations. And once you're satisfied that those parameters work, you're able to store all of that data in the tool library, and it's accessible at any time by right-clicking in the software and saying, bring this information into the procedure. And of course, that's in addition to the standard templates that we normally would use. Okay, so here's the third tool path. And the same thing holds true. You can see that in the bigger area of this vein, it knows that material is gone. So the roughing is just staying in the areas that have not been roughed out yet and where this tool can go. But even here, you'll see that I'm down to a 10 thousandths ball cutter, and still there's areas that haven't been machined out. So rather than keep going through all this, I'm going to open up another file where I already have that done. And this would be the next procedure where we're now going down to an 8 thousandths ball cutter, still using a roughing strategy. And you can see that this one also, it knows what areas have been done and what areas haven't. So it's taking the material out from the ends of these veins and in between the short area of the perimeter and at the very end of the teeth. So now we've successfully roughed this all out down to an 8/1000 ball cutter. And the next procedure is the 8/1000 ball cutter using surface milling by limit angle strategy. What that one does is that it kind of looks at this differently based on horizontal and vertical areas. So you can see that across here in the more vertical areas, I have a bilayer path, like a Z-layer strategy. And then in the more horizontal areas, I get a spiral collapse. And it is a very nice path. Now, this one technically did take it to 0, but just to reiterate some of the things that Ralph was saying about tool control, I made a couple of more examples here. This one is going to be a spiraling tool path. You can see that my tolerance is set to 25 millionths. And it's a true spiral, so there's no connections between lanes. And I also made an example here of a standard tool path with the same strategy. The only difference between these two is that this one is calculated with a 2/10 tolerance, which in most cases would be a pretty tight tolerance, but compared to 25 millionths, it's not so much. So now I turn on the 2/10 tolerance. We'll go to a top view, and we'll zoom in here so you can get a real feel for the difference here in the tool paths. You can see that the red cord length is a much longer cord length than the yellow micromilling path. So that's the difference between micromilling and a standard milling at a 2/10 tolerance. And I also have one more example, well, two more actually with this one. This one is our morphine between two curves. And what I'm doing is I'm machining this vein, and I'm giving it a guide curve on the left and a guide curve on the right, and doing a morph between the two to give a nice finish in each of those veins. And then lastly, I have the remachine cleanup. Now, the remachine cleanup also has no use for boundaries. It's able to go in and accurately see what areas need to be remachined based on knowledge of previous cutter as well as previous stock.
I think the one thing to note on this too is if you show that tool path again, John.
Yeah.
The system is intelligent enough to know what's vertical and what is horizontal. So it's going to do the verticals in a Z-level manner, and then it's going to flow along the floor all the way along because that's more horizontal cut.
Yep. Okay, I've just got one more example here. And this one is one of my personal favorites. It's our ability to maintain sharp edges, and I think it's pretty cool. Basically, in an example like this, we've got these little triangles that we need to machine, and if you can imagine a small cutter, we're running around these guys, there's an excellent chance that you could be rounding off the corners. If this needed to stay nice and sharp, the appropriate way to program this would, of course, be two-dimensional, where you could have a lead in, cut across that length, and a lead out, and then again a lead in, cut across that length, and a lead out. I think everyone would agree that's the appropriate strategy for this type of situation. And we can do it in a 3D environment. Basically what we do is we define the sharp edges. I'll just quickly go into this one and show you that what I've done is I've selected all of these vertical edges as being sharp. So when I calculate this, and let me just go ahead and go to the navigator and I'll play it for a second so you can see. as the tool comes down, it's going to do just like we would in a 2D environment. It's going to arc in, it's going to cut that length, arc off, and then do the same thing for each subsequent edge. And we have this ability not only with the vertical sharp edges, but also the horizontal sharp edges, which is handled a bit differently. But any sharp edge that we define in the software, the system is careful not to round it off. Not that the software would round it off, but sometimes various combinations of things can work against you to round corners off. Okay, I'll turn it back over to Ralph at this time.
Okay. Thanks, John. Again, we're showing some of the techniques for how to handle these micromilling machines and how to cut the parts the most efficient way, and attacking them the way that it has to be attacked to get the results that you want. This one here, this is just a couple of examples. This is a handy lathe machine. It's an actual lathe, and you can see the size of it. The next one was like a manufacturing work cell. John? John? Oh, there you go. This is a desktop factory where it's doing several different operations all on this little table here. So this whole market is definitely growing, and there's a tremendous amount of opportunity in this market, and quite a bit of investigation has to go into what you're looking for and what you want to result. So at this time, we're pretty much open for any questions. Again, just type in the question and we'll address the questions.
All right. Thank you very much, Ralph and John. If you do have any questions, please send them in, and we will be logging off shortly. But if something comes to mind, we encourage you to email to Ralph directly, and he promises to get back to you. All right.
Here's one question that came through is, how long have we been supporting the micromilling technology? I want to say 3 or 4 years we've been supporting this. We saw a tremendous opportunity, and we started development for the very tight tolerances and the tool control.
There's another question. All right, here's another question. How is tool wear accommodated for?
I think with the monitoring systems out there, again, I'm not an expert on the tools, on the machine side and the monitoring system. I think the monitoring system is monitoring the load of the tool. Also, there's some opportunities when creating these tool paths that, after so long we can go and re-inspect the tool with the laser and see if it's still within tolerance and then continue cutting, rather than cutting the whole job and finding out that, at the end it wore out. So, there's several different options to monitor the tool wear. And a lot depends on the machine manufacturer.
Okay. Another question, is the angle of determination between level cutting and lacing user definable?
Yes. Yeah, it's what we call slope control. You can define what you want as defining as based on an angle from horizontal. So from 0 to 30 degrees, you want to call that horizontal, and anything above 30 degrees, you want to call it vertical. You can specify that, and the software automatically takes into consideration the overlap, and so it doesn't just start in the next level down. It's starting at the same level that it left off at. So.
Okay, another question for you, Ralph. There was a question pertaining to the use of coolant during micro-cutting. Is it used?
Again, it depends on the type of material. Most of the stuff that I've seen that they've, when cutting, usually it's just air.
Okay. All right.
But again, I'm not an expert on that. There's, I can definitely check with our micromilling partners and get you some answers on that as well too.
Okay. One of the questions had to do with the Cimatron seats. The question is, do we have micromilling with our seats at Cimatron, or do we need something additional?
No, it's all part of the NC program. It's not anything that's extra. It's it's an upgrade that I believe came out in version 8.
Okay. Another question is, how is Cimatron handling the point distribution differently for the micromilling compared to standard milling?
Well, again, the new algorithms for the micromilling are, calculating the tool path at a much tighter tolerance. So we're laying down a tremendous amount of points. Rather than standard conventional, programs. Like John was showing on that spiral cut. A 2/10 tolerance doesn't sound like much, but you could definitely see where, when you're at a 2/10 tolerance, you're plus or minus 2/10 from the actual surface. So it's going to put a lot less points around that diameter than, when you're using the micromilling.
Okay. There was a question about plunge cutting. Is this possible? Is it doable? Plunge cutting doable in the micro arena?
Yes, I believe so. But again, it depends on the type of tool. I don't know. You definitely can do it. It depends on the type of material you're cutting and the tool that you're actually cutting with. It seems like every week they're coming out with new varieties and new coatings for these tools. I'm sure it's doable. I don't know exactly. Again, I'll check with our micromilling partners and have them get me an answer, and I'll respond to everybody.
Okay. There's a question about ultra short pulse lasers. Do you have experience working with ultra short pulse lasers, which can ablate material in very fine increments? If so, what are your observations, pros and cons of using a laser?
I'm not familiar with that at all, but I'll investigate that and see what I can find out and pass the information along.
Okay. There was a question here regarding general feeds and cutting speeds. What is achievable with micromilling?
Again, it varies. I'd have to talk to each individual machine manufacturer is going to be different. Again, it depends on, the material and the tooling that you're using. I'll definitely find that information out too.
Okay. How do you set machining parameters? Tool manufacturers, by tooling manufacturing recommendations, or did you develop them yourselves through trial and error?
What was the first part of that question?
How do you go about setting machining parameters? Do you rely on tooling manufacturer recommendations, or did you develop them yourself through trial and error?
Yeah, it's definitely you're starting off with the tool manufacturer, their recommendations, but then it's, you know, you're going to rely on experience as well too, in testing. There's tremendous amount of testing, you know, to achieve the results that you want. You know, in some cases we tried cutting it, you know, 4 or 5 different ways to hold, you know, the less than 1 micron tolerance that they were holding and the surface finish. So one tool you may want to cut it in a Z-level fashion, where another tool you want to maybe cut it in a lace or an upward only manner. So again, yeah, you'll have to work with from the tool manufacturer as far as their recommendations, but I would say that's a starting point. We're not going to come out of the box with recommendations on, you know, for a 3,000 diameter, you know, tapered cutter, and you're cutting, you know, stainless steel. You know, you should be cutting this way. A lot of the micromilling manufacturers have done a lot of testing and have that information, and they'll be able to help you as well too with the right tooling and, you know, the feeds and speeds. But once you get that information, you can store that information in our tool library. So every time you're going to use that tool, you're going to be using those feeds and speeds and side steps and down steps. So there's no, you know, next time you go to use it, you know, I have to re-punch it all in. But we're keeping all of that with our tool library. You know, the plunging and the side feed or the entry feed into the part. You may want to slow down a little bit, or if you want to break out, you know, you're breaking out of the stock. You know, we have all different options to store that information. You know, once you have the most and the best efficient way of using that tool, it's stored right within that tool. So you don't, you know, every time you use that, you have the right settings.
All right, we have a question here. What are the minimum hardware requirements to run the software?
The minimum requirements, you know, will run pretty much on any PC that you can go out there and buy today. Again, it's more of how many, you know, surfaces or how many, you know, how large are parts. You know, we're seeing some electrodes. We ran across electrodes that had 160,000 faces. Well, in that case, you're definitely going to want something that's, you know, pretty powerful to calculate. So, you know, PCs are getting cheaper and cheaper. RAM is cheaper. You know, I would say the very minimum requirements probably, you know, 2 gig of RAM and basically any of the PCs that you have out there. The graphics is important as well too. You know, our software, we support, you know, NVIDIA graphics cards. You don't need the high end. We support the low end ones. You know, so it can be a couple $100 for a graphics card. But today, pretty much any PC is efficient enough to run the software.
Okay. Ralph, there's a question. Can the software tell you how many linear inches have been traveled for a specific tool and or tool path?
Yeah, we can. We do track that. We also have an option that if you only want to cut for 30 minutes, or if you only want to cut for a certain distance with the tool, then we can put that in there in our tool library as, you know, the tool life, and it will intelligently go and change the tool, not right in the middle of a cut, but it'll go and intelligently change the tool and grab the next tool. So, yeah, we can monitor that as we're cutting and switch tools, or we can tell you what the total length of cut is.
All right, there was a question about the demonstration part. What was the total machining time for the gear programs, roughing through finish, and what was the material being machined?
John, are you still on?
Yeah, I'm still on. I actually didn't run a report on the length of time. I can get back to that person with that information. That when I'm done, I can find out exactly what it was and get back to them.
All right, thank you. Did it? All right, we're running short on time here, and what we would like to do is remind you that the presentation has been recorded. You will be emailed a link to the recorded version, which will allow you to listen to any portion you have missed or would like to hear again. And remind you that if you have further questions, you can send those to Ralph. We'll have a slide here that shows where you can send those questions. And again, this is Don Nelson, speaking for both Cimatron Technologies and Micromanufacturing Magazine. I want to thank you for your time and for participating in today's webinar.
Thank you.
Thank you.